Hello, and welcome to this lesson about engines. We're about to have a look at one of the most iconic parts of an aircraft that can play a fundamental role in determining its performance, the engine. Pretty much everyone knows what I'm talking about, or at least how to spot it, but pointing it out doesn't hurt, so here it is. Let's now have a look at some basic terms. The first term comes from lesson 1. Remember the four forces acting on an aircraft? Thrust is generated by one or more functioning engines on board. All aircraft engines give a push forward, as we will see very soon. However, the term thrust is generally used only when referring to a jet engine. So, what term is used for an aircraft with propellers? The term is power. Power in physics is the amount of energy acquired or lost in a period of time. The fuel flow is defined as the amount of fuel flowing to the engine in a period of time, generally 1 hour. It is measured in pounds per hour or kilograms per hour and gives a good indication of the rate of fuel consumption of the aircraft. Finally, the second and third laws of Newton. The second law states that mass times acceleration equals a force, so F equals m times a. The third law states every action generates an equal and opposite reaction. To give a quick example, when you're canoeing, you push backwards to go forward. The paddle pushes the water and the water pushes you in the opposite direction. We will soon be going to talk more in depth about each type of engine, but first I would like to explain how a propeller is related to power and how it produces thrust. There are numerous factors to consider when working with a propeller that affect its performance, and I will just name some of them. Rotation speed, that can increase the power output up to a certain point, thickness of the blades, twist of the blades, number of blades, and so on. During the first lesson, we discussed how lift is produced on a wing. The concept is pretty much the same. Create a shape that placed in an airflow disturbs it, receiving a push in a specific direction relative to the shape considered. To keep it simple, we can think of each blade as a wing, in most cases a twisted wing, that springs out of the same shaft. In this case, the speed of the airflow is made of two components. One is the speed of the aircraft relative to the air around it. The other is the speed perceived by the blades from the rotating propeller. Each blade is subject to a lift force, which direction is parallel to the direction of motion of the aircraft. The result is that the propeller, by rotating, collects air from the front, going at a certain speed, and shoots the same air towards the back at much higher speed. The acceleration of the mass of air is what creates the force we call thrust. I still haven't mentioned why we talk of power when dealing with propellers. To explain this, we have to go back another step. What makes the propeller rotate? We said that the blades all spring out of the same shaft. This shaft is put in motion by the engine that has an associated value called power. A certain value of power gives the information of how well, in a period of time, your engine works. The sole purpose of the engine with a propeller is to make the shaft rotate, so that the blades can generate the necessary thrust. Now that you know how a propeller works, we can talk about the first type of engine we'll discuss today, the piston engine. It's made of two elements, a propeller and a piston engine that makes it rotate. The piston engine is the same you would find in cars, boats, and motorbikes. By using a group of pistons moving inside cylinders, the air-fuel mixture drawn inside each cylinder gets compressed by the piston moving toward the top, and then ignited so that a strong expansion of the mixture will be pushing away the piston toward the bottom of the cylinder before being exhausted. The moving piston, connected to a gearing system, will drive a shaft that is linked directly or through a reduction gear to the propeller. We can summarize the cycle of a piston engine in the following stages: intake, compression, ignition, expansion, exhaustion. Because of its nature, piston engines tend to be heavier than jet engines for the same power output. They are somewhat limited in terms of compression capacity, especially at higher altitudes, where the air gets thinner. The performance they offer is a lot less than other type of engines, so they pose a clear limit on takeoff weights, climbability, and cruise speeds. Because they are cheap to run and reliable when used at lower altitudes, they are perfect for small planes, which do not require very high thrust and do not need to fly very high. Jet engine. When you think of the engine of an airplane, a jet engine is probably what comes to mind first. It's what we see fitted on airliners. They're an enclosed type of engine that blows a jet of high-speed air. A jet engine works similarly to a piston engine in the sense that the stages are exactly the same: intake, compression, ignition, expansion, and exhaustion. However, in a jet engine, they all happen at the same time in different areas. You can imagine a jet engine as a tube. The front part of the tube is where the ingestion of air, or intake, takes place. Its shape is generally designed so that the outside air can slightly reduce its speed and become less turbulent before going through the engine. After that, as we move deeper into the engine, we find the compressor stage. This is made of a series of rotating discs and static discs, put in sequence one after the other to compress the air. These series of discs are called rotors and stators. Rotors and stators are made of many little blades and use the principle of Bernoulli. So, as the air flows through the compressor, its speed reduces, but its pressure increases dramatically. Further in, there's the combustion chamber, where sprayed fuel is added to the compressed air and shortly after ignited. By adding fuel, we are giving air extra energy that will be used for expansion. A turbine is found in the last portion of the engine, where the burning air-fuel mixture is expanded through the use of a turbine. Mirroring the design of the compressor, a turbine is made up of many stages of stators and rotors, except they work in the opposite way. Using Bernoulli's theorem again, you can understand that by expanding the air, its pressure is reduced and its speed considerably increased. The final part of the jet engine is the exhaustion cone. Here, by using a specific design, the air pressure is reduced even more, resulting in a jet of hot air-fuel mixture into the atmosphere. The air exhausted from the engine has such a greater speed than the air that was initially taken in and that surrounds the engine that creates an equal and opposite reaction, a force that pushes the engine in the opposite direction, that is forward. There's an element that hasn't been analyzed yet. The compressor and the turbine are connected by a shaft. The expanding air in the tube keeps the turbine rotors in movement, which in turn, being linked to the compressor rotors via the shaft, will drive the compressor that will force air to go through the engine, which will reach the turbine and keep its rotor moving, and so on. A common variation of a jet engine is the so-called turboprop engine. It looks very similar to a piston engine and works similarly too. The difference is that what moves that big propeller at the front is a jet engine. The result sits between a piston engine, for the fact that we use a big propeller, and a turbofan engine, which we'll talk about very soon. While the use of a big propeller limits the airplane to lower altitudes and speeds, though still being a massive improvement from the piston engine, the cost saving compared to the more known turbofan make it a perfect candidate for a small commercial plane. It is now time to talk about the very famous turbofan engine. This is the one we commonly see on pretty much every modern passenger aircraft. Just as it does for the turboprop, the turbofan engine works the same way as a jet engine, but now the turbine drives both the compressor and the front fan, or propeller in a turboprop. The fan is a big rotor stage of the compressor that is put at the very front of the engine. Its size is bigger than the size of the jet engine and pushes a small portion of the air into the jet engine itself and the rest of the air around it, causing another stream of air to speed up, generating thrust. In both cases, what is used to generate thrust is not the jet engine itself, but the fan at the front. The jet engine's main job is simply to produce enough energy to keep the fan in high-speed motion. Jet engines and turbofan engines are very performing. Their power output is huge and they can work very efficiently at high altitudes and high speeds. Airliners fly at speeds that are generally between 60 and 85% of the speed of sound. At these speeds, a turbofan engine is the most efficient one. A pure jet engine is more effective at higher speeds, at or above speed of sound, which is why high-performance fighter jets normally have pure jet engines. Another example, for those of you who remember, is the Concorde, which used to have 4 jet engines. Since I have mentioned fighter jets, I will briefly discuss the use of afterburners. If you're wondering what they are, just think of the typical military aircraft with fire coming out of its rear end when taking off. And no, it's not because they use extra spicy fuel. Anyway, getting back to the afterburners, they're simply an additional exhaustion area at the end of the engine. Here, the exhaustion gases, instead of being released in the atmosphere, are mixed with more fuel and ignited once again to achieve even higher speeds before being released into the atmosphere. The final result? A massive peak in the output of the engine. On the downside, afterburners use a lot more fuel, which makes these engines not very profitable. Have you ever heard of an APU? APU stands for Auxiliary Power Unit, and it normally sits at the very back of the airplane fuselage in the so-called tail cone. So, what is it? Well, when you're in flight, the engines supply electrical power and air conditioning to the whole aircraft. But how about when the engines are shut off, for example, while you're boarding? I'm sure you don't have many memories of boarding a big hot airplane with no aircon or lights on. That is because the APU is running. The APU is a small jet engine that, instead of producing thrust to get the airplane in motion, runs to provide cool air and electricity. Obviously, the engine used for APUs is small and uses very little fuel compared to the average engines. The APU is also important in flight to provide system redundancy. If there is a problem with the engine generators or the air conditioning machine attached to the main engine, the APU can be used to provide power and air, even during the flight. I think we have covered all the basics of aircraft engine and you should be able to spot the type of aircraft engine when you see one. See you in the next lesson.